Let's talk about variation of parameters. We use this technique to solve the non-homogeneous differential equation y double prime plus p of xy prime plus q of xy equals f of x. We say non-homogeneous because this thing on the right side is not 0. As before, the general solution to the non-homogeneous differential equation will be y equals y sub p plus y sub h, where y sub p is one particular solution to this non-homogeneous differential equation, and y sub h is the general solution to the corresponding homogeneous differential equation, y double prime plus p of xy prime plus q of xy equals 0. This is called homogeneous because the right side is 0. So when do we use it? When do we use this technique called variation of parameters? We use undetermined coefficients, the technique we learned earlier, to solve y double prime plus p of xy prime plus q of xy equals f of x, when f of x is a polynomial, exponential function, sine, cosine, or some linear combination of these. Variation of parameters works in many other circumstances, but it's complicated, so it's not our first choice. Our first choice is undetermined coefficients. Variation of parameters is our last resort. First, we find a general solution y sub h to the homogeneous differential equation y double prime plus p of xy prime plus q of xy equals 0. We've done this before. Then we find a particular solution to the non-homogeneous differential equation. This solution will be of the form, now I warn you, it gets hairy, and I'm going to run through this quickly, but then we'll walk through it as we go through a problem, and you'll be fine. You'll understand it. Not when I'm talking about it now, but once we go over a problem. Okay, so a particular solution of the non-homogeneous differential equation is going to be of the form y sub p equals u1 of x, y1 of x, plus u2 of x, y2 of x. To find u1 and u2, solve the system y1 u1 prime plus y2 u2 prime equals 0. y1 prime u1 prime plus y2 prime u2 prime equals f of x. We could then use Cramer's rule to solve this system of equations, and you probably don't remember Cramer's rule, but I'll show you how it works out. So again, the solution to this system of equations by Cramer's rule is going to look like this. u1 prime is negative y2 f of x over w, u2 prime equals y1 f of x over w, where w is the determinant y1, y2, y1 prime, y2 prime. We call it the Wronskian. And then we would integrate u1 prime and u2 prime to find u1 and u2. Okay, now let's apply for a problem. Use variation of parameters to solve the non-homogeneous differential equation y double prime plus 3y prime plus 2y equals 1 over 12 plus e to the x. Notice this is not an exponential function, a sine or a cosine. It's not a polynomial. So we're not going to use undetermined coefficients. We're going to use variation of parameters. First, we find a general solution y sub h to the homogeneous differential equation y double prime plus 3y prime plus 2y equals 0. We call y sub h the complementary function. It will be of the form y sub h equals c1y1 plus c2y2, where y1, y2 is a fundamental set of solutions. So we've done this before. We know what to do here. Okay, so y double prime plus 3y prime plus 2y equals 0. R squared plus 3r plus 2 equals 0. R1 times r plus 1, r plus 2 equals 0 is the factored form of it. R equals negative 1, r equals negative 2 is the solution. So that means our two solutions to this differential equation, this homogeneous differential equation, are going to be e to the negative x and e to the negative 2x. And so those will be our two solutions. y1 equals e to the negative x, y2 equals e to the negative 2x. And y1, y2, e to the x, e to the negative x, e to the negative 2x is a fundamental set of solutions. In other words, they are linearly independent. That set is linearly independent. The general solution, y sub h, to the homogeneous differential equation is going to be of this form. Y sub h equals c1y1 plus c2y2. In other words, it's c1 e to the negative x plus c2 e to the negative 2x. Great, we've done that before. Now comes the hairy part. A particular solution to the non-homogeneous differential equation will be y sub p equals u1 of x, y1 of x, plus u2 of x, y2 of x. We find u1 of x and u2 of x by solving this system of equations. y1 u1 prime plus y2 u2 prime equals 0. y1 prime u1 prime plus y2 prime u2 prime equals f of x. We can use Cramer's rule to solve this. This is how u1 will work out. u1 prime, that is. This is how u2 prime will work out, and w is, what we said earlier, is the Wronskian. Okay, so we have this system of equations. y1 in this case is our first solution to the homogeneous differential equation, so it'll be e to the negative x. y2 is going to be the second solution, which is e to the negative 2x. And then we just have u1 prime and u2 prime. We'll find out in a moment what those are. And then y1 prime is the derivative, so that'll be negative e to the negative x. That's the derivative of e to the negative x. And y2 prime is going to be the derivative of y2, so it'll be negative 2 e to the negative 2x. Okay, so we have this system of equations. The variables are u1 prime and u2 prime. Let's solve it. Again, the right side is the right side of the non-homogeneous equation, 1 over 12 plus e to the x. Let's solve this using Cramer's rule. So when you use Cramer's rule, first you got to find the Wronskian, so let's go ahead and do that. So it's this determinant. y1 is e to the negative x, y2 is e to the negative 2x. We have y1 prime and y2 prime as the derivatives. When you evaluate this determinant, you get e to the negative x times negative 2 e to the negative 2x minus this diagonal, negative e to the negative x times e to the negative 2x. Multiply that out, you end up with negative 2 e to the negative 3x plus e to the negative 3x. In other words, it's e to the negative 3x. So that's the Wronskian. That's what's on the bottom of u1 prime. So u1 prime is going to be negative y2 f of x over w. This is y2. That's our solution to the differential equation. That's our second solution to the differential equation. This is f of x. So that was the right side of the non-homogeneous differential equation. This is the Wronskian, negative e to the negative 3x. And we have the negative sign out front. So when we simplify this, okay, the e to the negative 2x and e to the 3x, those just simplify, and that'll give us an e to the x on top. Negative signs cancel, and we're left with e to the x over 12 plus e to the x. u2 prime is going to be y1 f of x over w. y1 was the first solution to the differential equation, homogeneous one, which is e to the negative x. F of x we know, w is the same. So the e to the negative x and the negative e to the negative 3x simplify to negative e to the 2x. Because when you subtract these exponents, negative x minus negative 3x, that just is positive 2x. Okay, so we have negative e to the 2x over 12 plus e to the x. That's u2 prime. So we integrate these to find u1 and u2. u1 is the integral of e to the x over 12 plus e to the x. Oh, we're going to use substitution for this baby. U is 12 plus e to the x, and du is e to the x dx, and that's exactly what we have here. So notice we've got e to the x dx, and then we've got, that's du, and then we've got u on the bottom. So this is just du over u. Oh man, we know how to integrate that. That's the natural log of the absolute value of u plus c. In other words, it's going to be the natural log of the absolute value of 12 plus e to the x plus c. So u1, okay, we don't need the plus c. We want a particular solution. So we don't need the general solution. So u1 is the natural log of 12 plus e to the x, an absolute value. But since 12 plus e to the x is positive, we'll just write that as natural log of 12 plus e to the x. u2 is the integral of a negative e to the 2x over 12 plus e to the x. We're going to use substitution. Now we'll let u equal e to the x, and du is e to the x dx. So I'm going to rewrite this. I'm going to break this up. So e to the negative e to the 2x can be written as negative e to the x times e to the x. I've broken it up because this is our du. So we have negative u, and we've got the du here, over 12 plus u. So we have the integral of negative u over 12 plus u du. Oh my goodness, we need to do long division of polynomials. You saw that in the chapter on partial fractions. Remember that in second semester calculus? It was a long time ago. What we need to do is find negative u divided by u plus 12. So we're going to do this long division of polynomials. So it's negative u divided by u plus 12. We're going to multiply both sides. We're going to multiply this by negative 1. Okay, and we're going to subtract negative u minus 12, and that just leaves us positive 12. So we have negative u over u plus 12. It turns out to be negative 1 plus this remainder, namely 12 over u plus 12. So the integral, so u2 is going to be the integral of negative u over 12 plus u du. But we just found on the above line that this is the same thing as the integral of negative 1 plus 12 over 12 plus u. So the antiderivative of this will be negative u plus 12, natural log u plus 12, plus c. Let's replace u with e to the x. So this is negative e to the x plus 12 natural log of e to the x plus 12 plus c. In other words, a u2 is going to be negative e to the x plus 12 natural log e to the x plus 12. We can forget the plus c because we want a particular solution. So particular solution to the non-homogeneous differential equation looks like this. Y sub p is u1 y1 plus u2 y2. Let's plug in the stuff we know. So that's going to be, in other words, natural log 12 plus e to the x times e to the negative x plus negative e to the x plus natural log 12 plus e to the x times e to the negative 2x. Thus, the general solution to the non-homogeneous differential equation, this is the one we've been working with, is going to be y equals y sub p plus y sub h. Y sub p is one particular solution to the differential equation. Y sub h is a general solution to the corresponding homogeneous differential equation. And y equals y sub p plus y sub h. Again, so we've got y equals this. That's our y sub p plus y sub h. Okay, it's going to be 12. Natural log 12 plus e to the x times e to the negative x plus negative e to the x plus natural log 12 plus e to the x times e to the negative 2x plus c1 e to the negative x plus c2 e to the negative 2x. Whew.